Hi, welcome to Perceptual Optics, 4th class Frames of Consciousness. As you transition from sleep into wake, there's a ramp-up period where you go from 2 to 4 hertz up to 10 to 40 hertz. And I think that you can actually sense this increasing frequency. Like as soon as you wake up and you're still laying on your bed, maybe you just open your eyes briefly and then close them again. I can sense this increasing rate, and it definitely feels like about 5 to 10 hertz, but it seems like it goes a lot higher than 10, like maybe 20 hertz, like it's ramping up to a rate that I can't even continue to pay attention to it. And what people report in this little stage here is that it seems to be these random flicks of just unrelated imagery of probably memory that the brain is just shooting like just to kind of jolt you and basically get out of this hyperpolarized sleep state where you can start getting incoming stimuli and pay attention to the real world again. So this is the wake section here in the middle, and in this example the person fell back asleep after 10 seconds of being awake. At a small enough temporal resolution, consciousness has to be discrete. It would take infinite brain resources to print the full 3D consciousness every nanosecond, or every infinitesimal moment of consciousness. So at some level, consciousness must be discrete as a matter of fact. Now, what is that rate, and is it variable, and are there multiple rates going on at the same time? I would say probably so. And we'll look at this paper here by Van Rollen and Christof Koch that talks about frames of consciousness, in which they talk about, in general, 10 hertz frames noted in the visual cortex, but they could also see theta of the hippocampus and gamma waves as possibly having something to do with conscious frames also. This first quote from the Christof Koch paper blows me away because it's pretty much exactly what I think happens with consciousness. And he says, conscious perception might well be constant within a snapshot of variable duration. So in other words, these frames of consciousness can dynamically change in duration, or which would also be frequency, and they're constant for that particular snapshot. And I would take it just one step further and say that these snapshots are generally 2D planes at some attitude and position within the real world schema, and that they can walk around as you move your attention, and they can change attitude. And so all that together would kind of give you a picture of how this context of consciousness is going on. He also said the slow waves, 4 to 12 hertz, would define the span of memory on which the fast waves would inscribe the memories themselves, depending on the particular ratio between the slow and fast wave frequencies, up to 7 items. And later he says maybe more like 4 could be multiplexed in this manner. One thing I would argue is that it may be that on a single ring, in other words, a single slow wave cycle, there are 4 to 7 stops along the ring path, and each one is encoding a disparate qualia. So one would be dedicated to encoding the sense of smell, one would be sound, one would be balance and inertia, one would be sight, one would be your mood and your sense of self, and then together that one frame of consciousness would have bound all the disparate qualia together. Might not be the only way to look at it, but it's an interesting concept. He also said alpha waves tend to be more global, which is true, traveling throughout cortex, and the gamma waves are generally going to be more localized and involve neuronal populations within one or occasionally a few cortical areas. And he says this fits well with the idea that slow waves could constitute the context of consciousness and fast waves the content of neuronal representations. And once again, that's just kind of blows me away, because it's like that's exactly what I think too. That the context is the three-dimensional shapes or screens of consciousness, and the content is like this two-dimensional pixel paint. So sort of like a sphere shell around you, and you can look out in any direction, and any direction has some pixel that's colored a certain color, and based on the size of the feature, you can infer how far away it is. But basically the two-dimensional thing would just be concerned with the three-dimensional vector orientation of each ray, or in other words, the pixel, and not so much the voxel. And so this stuff here would be the content, and it would be refreshed generally at a faster rate, such as 40 to 80 hertz, than the context, which would be the frames of consciousness proper, the three-dimensional shapes, your attention, going at generally a slower rate, like 10 hertz, although I think it can be variable from 2 all the way to possibly 1,000. This is a summary of the Christof Koch paper on frames of consciousness, and you notice 100 millisecond is a duration that generally, when two things fall in that time duration, they're going to be perceived as happening at the same time. And then if it happens outside of that, they'll be considered as two separate events. So, and he says, so that's like a computational window, but also he thinks this is actually the length of the frame of consciousness, and it stays static for that 100 milliseconds. And he also found 25 milliseconds as a number of interest, which could have more to do with what we were talking about, the paint or the content of consciousness. So like I said, I would posit that consciousness is basically two components. You have this sphere shell around you, this paint rate, sphere shell around you that's got pixels, and based on the image that's printed there, if you see a person that's a certain height of theta, or a certain width of, height of phi, or a certain width of theta, you know what actual size the person is, so then you can judge how far away they are, which might be prefrontal cortex using that information and making judgments based on prior experience. But in general, it's just this 2D shell, and it's at a high frequency, like 40 to 80 hertz, and it can be independent of the frames of consciousness proper, which would be like the shape rate. And I say shape because a lot of times as you bring your ventral visual stream to bring its attention to certain objects, that it's a certain shape. A wallet or a speaker has a certain shape. Like I said, this is generally 10 hertz, but could be 1 to 1,000 hertz variable. And then the paint would be postulated to be the dorsal visual stream. Of course, a lot of times people think, well, color is in the ventral what path, and there is region V4 there, but I think that's handling color in terms of remembering or associating a color with an object, whereas I think the dorsal stream, in particular the termination in the posterior parietal cortex, is going to be handling the creation of perceptual color. And they have done one study where they showed a person two images to one to each eye, like two politicians or something, and they would flick between seeing one and then seeing the other. It'd be 100% of the left eye and then 100% of the right eye. And they would go back and forth, and when they applied transcranial magnetic stimulation to the posterior parietal cortex, they were able to make one of the perceptions last 2 or 3 times longer before switching back over. So, and that was basically influencing how long they saw 2D locational color. So it would seem to me that posterior parietal cortex very well may be involved in color perception. A lot of the time we look at the various brain waves and we think that, oh, alpha is involved in this and theta is involved in that, and delta is just when you're asleep and stuff like that. But I think it's really more of a real-time dynamic transition from one to the other, and it really doesn't have anything to do with all that. I think the brain varies the rate of consciousness of these frames based on what it needs. So if the task at hand only needs 2 frames a second, that's only going to print out 2 frames a second. If you're listening to music and you're trying to tease out little bits of detail that require 500 or 1,000 samples per second, then all of a sudden you need ostensibly 500 to 1,000 frames a second. And so you can, if you just dynamically let the brain use the rate that it needs to use, then it really isn't about some magical frequency. It's just whatever it needs to get the job done and to understand the world at sufficient temporal resolution. So reading, like I said, would only need 2 to 10 frames a second resolution. Christof Koch talks about that, or at least about the 10 hertz. Vibration, though, like something's buzzing on your hand, you're going to need 10 to 50 frames a second to represent that, ostensibly. If you're trying to track something that's moving, you probably need 20 to 80 frames a second. And if you're paying attention to music, you would need the highest temporal resolution, possibly as high as 100 to 1,000 frames a second, but also as low as 1 or 0.1 frames a second, or phase locking, I guess, per second, because the frames of consciousness probably wouldn't go quite that low. But if you're paying attention to a very slow beat, then it could transiently align to some of those beats. As we continue, the next slide's got some more. So the feeling of qualia would probably require 5 to 50 frames a second, fairly high, and that's for giving you the feeling of a smell, or you dip your foot in cold water and you feel the coldness, or you have a sensation of your current mood or your sense of self. Any of that kind of stuff is that the feeling is created with these frames that are probably 5 to 50 per second. When you listen to speech, it's going to be a fairly high temporal demand, so maybe 40 plus frames a second. If you're walking down a trail, maybe you can get by with 20 or 30 frames a second. And if you're tilting your head from left to right, it really doesn't require a lot for that, so maybe even just as little as 2 to 5 frames a second. Because there are limits to how much we can fit within attention in any given moment or within any given 100 millisecond frame of consciousness, the brain uses a lot of top-down expectation to kind of fill in the gaps. And like that's including like for your blind spot, which could also be bottom-up processing. Basically, the top-down is like you've got certain models of the way the form that certain objects should have, the shape that they should have, the shape that a certain scene or room should have, its layout. Those are things that you've learned, and it's kind of top-down filling in the details, like from the prefrontal cortex going down to the posterior parietal cortex. Bottom-up is referring to like the real-time sensory input that's coming from your eyes and ears and body going up to your brain and going through like visual cortex 1, primary visual cortex, primary somatosensory cortex, primary auditory cortex, and going up towards the posterior parietal cortex, where they're kind of blended together, so to speak. That's bottom up. So you got both of these things going on, and the point is that we might kind of halfway hallucinate that we really have the whole 3D scene, whereas maybe a lot of it's just the top-down fact that we already have memory and expectation of what should be there, and so we don't question it, even though it isn't actually being drawn. Maybe it's just, slightly triggering these old memories and expectations. But there's only so much that you can fit within attention And especially within one cycle of consciousness, 100 milliseconds or zero point 0.1 seconds, you can probably only fit 4 to 7 items of focus within that little moment. So this is looking at like nested or layered or iterated cyclization, because these action potentials here of this mouse or rat look pretty smooth, but if you look at it at a very fine time scale, they're still discrete. It's these action potentials that are happening at certain specific times. It's not continuous. It's specific times. But then this is their normal activity, and then if they're given ketamine, which is an NMDA antagonist, then it basically hyperpolarizes neurons, and especially in the retrosplenial cortex, layer 5, and opens up HCN1 channels, which cause this kind of 2 hertz frequency grouped action. So you get these action potentials bunched together in these little bunches, and the bunches are happening at about 2 hertz. And so this would probably feel to the rat very much like he's able to see the individual frames of consciousness, because he's cyclized the smoother activity into something that's very cyclic, not only on the individual action potential level, but groupings of action potentials are also cyclified here, or cyclized. Like I said, this is retrosplenial cortex. You can also get dissociation, such as between somatosensory cortex and retrosplenial, where when the retrosplenial is silent, the somatosensory is most active, and that could be behind the experience of dissociation, where it feels like you're floating off or viewing your body from the side, or you're not able to interact directly with the body. The body's doing its own thing, independent of you. That might be because of this kind of cross correlation or anti-correlation between the timing of the peaks of these 2 different brain regions, because of this hyperpolarization, this NMDA antagonism that was caused by ketamine and cyclification. And that's kind of how sleep works too, is that it hyperpolarizes neurons, so they start, basically once they get hyperpolarized, they have to fire a little bit, so you get this global activity at 2 to 4 hertz, which tends to shut down, letting these more spontaneous or more intermittent stimuli, like auditory stimuli from the outside world, come in. And that's why, part of the reason why you don't hear stuff when you're asleep is because the neurons got hyperpolarized, and they're not letting these more transient signals come through where you can pay attention to them. I forgot to mention in the last slide that any NMDA antagonist, and NMDA is a receptor for glutamate, which is the main excitatory neurotransmitter of the brain, of the cortex. So any NMDA antagonist, whether that's alcohol, ketamine, and also pretty much any GABA agonist, GABA being a chief inhibitory neurotransmitter. So you agonize that, it's kind of similar to antagonizing glutamate NMDA. Both of those tend to hyperpolarize neurons and set up cyclization, and so it's going to be easier to observe frames of consciousness with any of those kind of compounds. This next slide, concept cells, is the same thing as Jennifer Aniston neurons or grandmother cells, cells that are going to fire invariantly for some given concept, whether that's a person, whether that's an abstract concept, whether it's a particular shape. You get these concept cells. And they're all about recognition, understanding what something is. If you're talking fusiform gyrus in inferior temporal lobe, lateral occipital cortex, that information could arrive maybe 80 milliseconds of lag and maybe 15 to 30 milliseconds of identification. If you got to go all the way to the prefrontal cortex, you may have 100 or 120 milliseconds lag or 150 milliseconds lag. and then the 50 to 30 milliseconds of identification. So it always feels to us like we can identify things super quick because we're noticing this 15 to 30 milliseconds, and we're not noticing how long it takes to go through the unconscious channels of the brain first. When you're shooting video, you have to align the audio to the video, and they use a clapperboard to do that. When this clap stick comes down on the board, it makes a noise, and you also have video of exactly when they touch, so you can align the two temporally. So I think the brain also has a clapperboard, and I think it's, instead of just being one single time, I think it's continuous, like it's clapping, like, 100 or 10 times a second, and in a sense 1,000 times a second, because like this zero-dimensional point is moving around along a ring path. But any one cycle of consciousness, the whole ring, is going to be more like 100 milliseconds. So what is the brain's clapperboard? Well, probably it's the thalamocortical resonant circuit, because you have the two components of the thalamus, which is the center of your brain. It's the relay center, letting sensory information from your eyes, your ears, your body come through to your cortex. It has to pass through there first. So that's specific nuclei information. Non-specific cells in the thalami are more global. They have a global reach on the brain, and they seem to be more with context, and possibly the frequency of the frames of context or frames of consciousness. If you have your eyes closed, your proprioception will tell you where your left hand is at. And then if you open your eyes and vision says it's slightly to the right of what you thought, then proprioception is going to update its signals or update the location of the proprioception hand to be in line with the location of the visual hand. And so that's called visual capture. And in general, vision trumps any of the other qualia as far as aligning things in location. Now, when we talk about aligning things temporally, that's where the thalamocortical resonant circuit would probably come in more. As we discussed in the last class, there are these constant transient attention shifts, maybe 4 or more per second, where the bank is moving from one thing, like your phone, to another, like your torso and your posture, to another, like you're tilting your head, to something out in the distance that you observe. So the bank is walking around all the time within the real-world schema, perceptual space. You got these transient attention shifts. The brain's attention can shift rapidly between different sensory modalities, also, like touch, proprioception, sound, sight, smell, taste. These transient attention shifts can occur on different perceptual spatial scales, ranging from a single point to a plane to a swath of volume. They can also be triggered by various stimuli, such as external events, internal sensations, or even slight movements of the body. Recent studies, such as this one here, provide insights into the neural mechanisms underlying these transient attention shifts and their role in perception and cognition. So basically, the last class was talking that the bank can move around and bring conscious focus to specific things transiently. And because you have to shift your attention constantly between these various things, you can only have so much in any given moment of conscious experience and conscious attention. These are the planes going through your head. So coronal is kind of like if you're wearing a headband, it's kind of that plane. You've got sagittal is kind of going from your nose to the back of your head, and from the top of your head to the bottom. It's that plane there. And horizontal is also known as transverse, and it's this kind of flat plane. So when we talk about attention, we can mean a few different things. One meaning of attention is what point am I looking at? Another meaning of attention could be what point of sound am I focusing on? Like you could be focused on where a sound is originating from. And those are useful. But what I'm talking about in terms of alignment is can be independent of that. So the brain can be doing its alignment ring at some location that is different than the location of the eye of the avatar or what the avatar is looking at. So that's okay. That's allowed. And it's not like that wherever you're looking has to be um, the alignment point for the brain. In fact, it doesn't seem like it usually is. So the bank is proposed to be the aligner or tether of the real world schema and imagination schema. So it's kind of like a go-between, or it's like the bank is tethered to the real world schema and the imagination schema is tethered to the bank. But if you have a single plane illuminated in the bank, then the real world schema can be mapped to that and the imagination schema can be mapped to that. And that plane can rotate within perceptual space, like the whole bank can rotate, but also the selection plane from off of the bank can rotate. So you got like multiple different kind of 3D rotations that can go on at the same time. Within a single cycle of consciousness, in other words, 100 milliseconds, you're going to first start with a zero-dimensional point of alignment. And at each millisecond, this point is going to move along a predefined path selected from the bank. And over the course of like 100 milliseconds, it's moved 100 times and traced out a whole ring. So that's the next slide. So here, a full frame of consciousness is shown in terms of the alignment. So you have the whole ring, and the next slide it's going to grow into a plane like this. Basically, this ring path will become kind of a circle plane. So this is a later stage in the phase of a single cycle of consciousness, and a whole frame, or basically this plane, is now kind of instantiated off of the bank, and it's aligning the worlds and giving an understanding of 3D space, because this thing's dynamically rotating all the time from cycle to cycle of consciousness. It's 3D rotating, so to speak, and it's slicing through this isometric model of the world, this real world schema, and because it's able to highlight which voxel is along the ring path and which voxel is on this plane, and because it's dynamically rotating, you get a very good sense of 3D. And I think that's a large part of why we're able to understand 3 dimensions so well, is that the brain's just all the time practicing and forcing itself to select which voxels lie along a certain plane or along a certain ring path. And the next slide will consider 3D volume, although I'm not sure that the brain actually uses the full 3D volume for alignment purposes, so it's a little bit speculative. So here you could envision that the whole 3D schema is now experienced, and that there's some bank overlaying it, and every single voxel within here has been mapped to a certain voxel on the bank at some rotation and to a certain voxel within the imagination schema. So we'd be talking about millions, if not billions, of voxels that have now been mapped between the 3 worlds. Like I said, I think that's a little bit too computationally expensive to ask the brain to do in every cycle of consciousness. So I think that over like 1 second of consciousness, you have 10 frames. Over that, the frames walking around within perceptual space, you kind of hallucinate or get the understanding of the whole 3D volume. But it's certainly possible that the brain is able to map, in terms of a 3D space, map all the voxels between the 3 main schemas, being real world schema, bank schema, and imagination schema. But like I said, it seems to be more of the 1-dimensional and 2-dimensional nature within a single cycle of consciousness. So if we consider the 1-dimensional and 2-dimensional aspects, we can state this theory here that intracolumnar traveling wave activity corresponds to one-dimensional style alignment, whereas where a zero-dimensional point smartly travels along a set one-dimensional path, a ring, intercolumnar standing wave activity corresponds to 2D style alignment, where an entire surfacial shape is instantiated at once. Inhibitory neurons are thought to help modulate this activity. Nonspecific nuclei in thalami are thought to modulate frequency changes of the cycles in real time. These waves might also happen in or be guided by hippocampal, dorsal, ventral traveling waves, which can morph into standing waves. So the table here is basically saying, okay, if we look at if we're experiencing one-dimensional alignment between the schemas, that's probably a traveling wave, a smart traveling wave, and each millisecond is using neurons that map to a specific voxel point, zero-dimensional point, and over 100 milliseconds, it's moved 100 times and traced out a whole ring. And within the column, you can see maybe a traveling wave from one part of the column to another of the various neurons. That's getting down pretty small and pretty speculative, but it could be. Because if you got traveling waves, you would have more of a duration, which is kind of what you see with ring alignment, one-dimensional. And if you had standing waves, which you can transition from one to the other, if you have standing waves, it would make sense to be more like this two-dimensional, all at once instantiation of this frame, now this frame, now this frame, and depicted here is actually 3 cycles of consciousness. So that would be 0.3 seconds or 0.1 second each frame. Whereas here, this is just depicting one frame. This would probably need to be over the course of like 2 or 3 seconds or even 4 seconds because the person's walking, so it would probably take at least 4 seconds for them to get from here to there. So these would be a very slow kind of alignment. And it may be that there's multiple frequencies at once going on to align the brain. And basically what it would do is it would use a specific orientation of plane and a specific ring shape path at any given moment, regardless of the frequency. And all these are, the shape and the orientation of that plane are changing dynamically in real time. And basically the multiple frequencies would just have to, they would have to behave according to what the current moment attitude of the plane is and what the current shape of the ring path is required to be. So that would be what would align multiple frequencies. But yeah, so that's one cycle there depicted. And as you move your body down the trail, what was a coronal ring around the body is now a helix going down the path. So kind of the same thing, ring or helix. But yeah, so that's demonstrating like could be traveling waves, this could be standing waves. So why would the inside of cortical columns, of which there are, I think, 100,000 roughly in the brain, why would the inside of cortical columns be a good place to serve as the correlate of the rings or the frames of consciousness? Well, for one, you have this thalamocortical resonant circuit, and you have nonspecific cells of the thalamus and specific cells of the thalamus converging on specific sets of neurons in the cortex. And when they simultaneously send signals to a particular neuron, of course it's multiple neurons at once, that set of neurons is much more likely to fire, and it's greater than just the summation of the two inputs. So you get kind of this ability to transiently morph your attention from one thing to another within the whole cortex just by using this circuit. And like I said in the last video, each cortical column, if we just say 50 neurons and let them be this sort of binary bit storage system, like for example, if you have an 8-bit JPEG image from a camera, then that can store 250 possibilities or levels of a particular color, like a red channel, green channel, blue channel. For each channel, you get 256 increments of brightness, like how red is it, how green is it. That's because 8 bits binary can store 256 different combinations. If you add a few more bits, up to 14 bits, you're now dealing with a raw image, and you can store, I think, 16,000 or something like that combinations. So exponentially more combinations are available. So if you bump it up to 50 and just take 50 neurons, now you can represent well over a trillion, possibly 100 trillion or 1 quadrillion. I'll have to look that back up. But you can store well over a trillion combinations with just 50 neurons. So, if you take 50 neurons from each of the 100,000 cortical columns, then we're talking what? Basically 5 million neurons taken out of the brain for each cortical column to have its own representation of the entirety of perceptual space and be able to map to voxels. So I think that's a powerful way that the brain could do these rings and do these planes and do this binding, brain-wide binding of all the qualia and all the regions of the brain. This slide is just some more information on, intracolumnar cortex regions as being the correlate of the rings or the bank alignment, and got some citations there. Alternatively, one could consider the hippocampus, in particular the dorsal ventral hippocampal axis, as a correlate for the rings. Basically because you have these theta waves that travel from the dorsal end to the ventral end of the hippocampus 7 times a second roughly. As you walk down a trail, the faster you go, the faster the waves go. The slower you go, the slower they go. Even if you're playing a video game, the faster the avatar goes in the video game, the faster these waves go. So there's some correlation, definitely a sort of spatial thing. Obviously the hippocampus also does memory, episodic memory, and also looking for like salient, unique aspects of each moment of consciousness. So, the hippocampus could be part of the creation of the rings, kind of as a guide. Maybe it's a correlate, but I still feel that the cortex, the individual columns of the cortex working together is a better correlate for the bank and the rings. Like the actual drawing of the rings, I should say, and using it to align to the other two schemas. Because like I said, I think the bank in general is going to be stored distributed, but more so in the lateral occipital cortex, fusiform gyrus, inferior temporal lobe, and maybe also some of the prefrontal cortex and posterior parietal cortex. So this slide is just looking at a person that's walking down a trail, and coronal rings around their body would change into a helix or a helical path, and that would be like one cycle of consciousness, a very slow sampling of it. Like I said, probably about over 2 or 4 seconds of time. This is illustrating that the frames of consciousness can morph in their shape from one frame to the next. So you could start with this more spherical frame, and then the bank could walk forwards a little bit and morph to a slightly more planar shape, and then finally it could walk forward again to the next frame of consciousness, and that frame could be perfectly planar, and it could be the face of the cube of the bank. So you've gone from the sphere to the cube face of the bank. And I think this happens quite a lot in consciousness, that there's this constant morphing between one shape and another. That's what it kind of looks like. This slide is the real takeaway of this video, and it's basically illustrating that when you create new frames of consciousness, you don't want them to occur at the same location as the previous frames, because if they did, it would kind of build up and be muddy, and it wouldn't be good for working memory or comparisons, things like that. So I propose that there are 3 ways that you can make sure that there's offset between old frames and new frames. So the first option I call walk, And I don't mean you walking somewhere, I mean like the bank walking, or you're walking your attention from one object to another object within the real world schema. So it's basically the bank or the frames of consciousness are moving around, walking around within the real world schema or the imagination schema as you move your attention from, say, your phone to your torso and then back down to the phone. The bank would move from one to the other. So you'd have two frames here at the phone, one frame in the air, one or two frames at the torso, maintaining balance, one frame at the air again, and then one or two back on the phone. So because the bank moved around, the new frames were always at a new location. So that's one mechanism. The second mechanism is what I call self-motion. So in other words, you are walking down a trail, therefore your body schema is moving relative to the environment schema, and each new frame of consciousness can be placed at a new location. The third option is what I call kick out. And so this is like if you're stationary or you're listening to music or something like that where the frame rate is extremely high, you need to basically kick the old frames out artificially. So you artificially move them away at some velocity in some direction. So because when you're listening to sound, the rings or the frames are being instantiated really fast, especially for some of the higher pitched notes or the vocal, some of that stuff, like when they're singing a word, the frame rate of these frames goes up transiently very, very high. And so to prevent there being mud, you've got to kick out the old frames. So basically you'd have this one frame here, and then 20 milliseconds later or 10 milliseconds later, you're painting a new frame of sound, so you want to kick the old frame away. And then in the next moment, here the new frame can take the same location, so it needs to kick both of those two frames even further away. And as they get kicked away, they also fade over time. And so you can have this new frame always assuming the same location and not moving, and yet it doesn't get muddy because the old frames get kicked out. And one experiment you can do is try listening to a song with your eyes closed and then pay attention on the last note of the song. Once there's silence, see if there is some directionality to which way the last note of the song is moving. And that sounds crazy to think about, but as music is playing, you're making this mental imagery, pretty much subconsciously, but you're making this mental imagery of either the person singing or of the concepts they're singing about, something to that effect, maybe of the band playing. So you've got this imagination schema going on, and as soon as they play the last note, it gets suddenly silent. So now it's not having to really print stuff anymore, and it's easier to recognize the directionality of which way that flow or kick out is going. And you'll probably notice that you can even kind of see it going away for maybe 1 to 5 seconds after the note has ended. And you'll notice that the directionality can be different at different times that you try that experiment. So the flow will be, generally it's going somewhat axial or normal to the plane of the ring or the frame of consciousness, but relative to your body, that may be going out of your belly, it may be going upwards, it may be going downwards, it may be going behind you, it could be going off at some funny angle. So that's kick out. And so that's actually pretty interesting. This slide is illustrating that the cortex is postulated to be able to reach down into the brainstem and in real time control the rate of the frames of consciousness by use of these varying levels neurotransmitters. So serotonin is one that's kind of long-lasting. I think they say days to hours, kind of up or down modulation of the rate of frames. There's also norepinephrine, which might be like minutes to seconds. There's dopamine, which I think is minutes or seconds range, and acetylcholine, I think is seconds or milliseconds somewhere. But basically, there's a gradient of how fast various of these things act and how long they act. But basically, the idea is that the cortex can reach down into the brainstem, activate these specific nuclei, for example, pedunculopontine nuclei, PPN. LDT is lateral dorsal tegmental nuclei. Those are acetylcholine nuclei in the brainstem, and they reach up to the nonspecific cells of the matrix cells of the thalamus, and that reaches globally to the whole cortex. So, by sending signals to PPN and LDT, you can kind of modulate the whole cortex, or the rate of, theoretically, possibly the rate of frames of consciousness. And there's also the Raphe nucleus for serotonin. There's locus coeruleus for norepinephrine. You also have like orexin neurotransmitters. So, the ARAS, the ascending reticular activating system, is implicated in waking up and helping to increase from slow delta waves to more of this 10 hertz to 40 hertz kind of frequency that's needful for paying attention to the real world and for being awake. So, for example, like in the little image there, when he's pressing his foot down on the gas, that could be causing the frames to be 10 hertz a second, or 10 frames a second, 10 hertz. And then when he takes his foot kind of more off of the gas, then it's only like 2 frames a second. So, and that's what I think the cortex is doing, like all the time in real time. It's changing, that quickly between one frequency and another frequency for these frames of consciousness. In the thalamus, 2 subpopulations of neurons exist. You have the nonspecific network, known as the matrix cells, and you also have specific cells. The matrix cells, or nonspecific, is going to be your reticular thalamic nucleus, also your intralaminar nuclei, and your midline nuclei of the thalamus. And then specific nuclei would be like the lateral geniculate nucleus, the medial geniculate nucleus for sound, things like that. So, and in this quote, he's saying that these loops could maintain fast thalamocortical waves of activity, and the gamma would correlate to the sensory or the content of consciousness, whereas the non-specific would correlate with the context or the screens or the frames of consciousness. You also have Rodolfo Enos proposing that the transient joining of specific non-specific nuclei, as they send action potentials to the cortex, if both of these alight upon a single neuron, it's going to have a superlinear effect. In other words, more than just adding the effect of the 2 inputs. So the neuron is going to almost certainly fire, and it's layer 6, so it's going back to the thalamus and kind of setting up this resonant circuit. So, Rodolfo Enos believes that this is where the brain is binding disparate qualia together, and that's pretty interesting. This diagram is showing you this. So you've got the specific nuclei of the thalamus and the non-specific nuclei, which the non-specific have global reach and the specific have specific reach, local. But where they happen to simultaneously fire on the same cortical neuron, it's almost certain to send a action potential back to the thalamus and set up this resonant circuit, which is, it's transient. So, just for a little bit, and then, you shift your attention somewhere else. But this allows you to move your attention to any one of these circuits. So basically there would just be, I guess at least 100,000, but probably millions of these circuits going from the thalamus to the cortex. And this allows you to basically bind the whole cortex together by, like, which one are we resonating right now? Which regions of cortex which neuronal ensembles are we resonating in each moment. And that's thought to underlie consciousness and binding. I may be being overly speculative here, but it would be nice if the nonspecific nuclei had something to do with the bank, possibly with driving the frequency of the bank frames, in other words, the main frames of consciousness, the 10 hertz generally, but variable from 1 hertz to 80 or possibly 1,000 hertz. And then specific would be driving the content of consciousness, the paint, the two-dimensional sphere shell around you of color, and locations like for sound and things like that. It's more locational, and then this would be more understanding what something is. Of course, from here I'm just saying that the rate would be modulated, not that the actual bank is flowing through that neuron or something. Because like I said, I think the bank is stored by long-term potentiation distributed across the cortex, but largely the terminal of the visual what stream, the ventral what stream, which, like I said, lateral occipital cortex, inferior temporal lobe, fusiform gyrus. That's largely where I think the bank is located. And you know, the bank would be able to be part of these neurons that are participating here. So that's pretty interesting. Let me see if over here we've got anything interesting. So Francis Crick was co-discoverer of DNA. He felt that neurons synchronized in 40 hertz oscillations, such as seen in this circuit, could serve as the neural correlates of consciousness. He worked together with Christof Koch in putting a paper together on that. So big names, and also Rodolfo Enos considers this a primary circuit for consciousness. So pretty interesting, pretty important. Within photography, you have the exposure triangle. When you move from photography to videography, you have to add frame rate and some other parameters. And then when you consider consciousness, it's a lot like video. You've still got all that stuff and probably a retina shutter speed of about 1/50th of a second. The frame rate can be variable from, I would argue, 1 or 2 frames a second up to 40 or 80 or maybe even as high as 500 or 1,000 frames a second for transient attention to music. But also within consciousness, you've got this other stuff. So the screen of the movie can move around, unlike videography where it's just a TV screen that stays fixed. In consciousness, I argue that the 2D slices through the 3D isometric models of the world can walk around and change shape and change attitude, in other words, rotation, orientation. So that's a big component of consciousness, I would argue, that's different from videography. And the display of each of these frames of consciousness can change, although I have this luminosity graph showing that, you know, over 0.1 or 0.2 seconds you lose most of the luminosity of the frame, but you still have a little bit left for working memory and stuff. And this is obviously just postulation there. Also often required is a particular frame shape. So, you know, the frames of consciousness, what is the shape of the outline of the frame? Is it a square outline? Is it a circle outline? Is it a squiggly circle? Is it a triangle? Is it Sonic the Hedgehog? You know, you got all these different shapes that the perimeter could be. And if instead of a standing wave, you have a traveling wave where you're moving this zero-dimensional point over a ring path and moving it 100 times in 0.1 second, like moving it 1 time every millisecond, okay, then how long did it take to draw the perimeter of that so-called frame of consciousness or cycle, which, you know, like I said, it could be more like a helix when it has some duration. But how long within the cycle of consciousness are you spending drawing the perimeter versus flushing it out and other stuff? This is a very interesting diagram from this source here, and you can see that when the soccer player is focusing on the soccer ball's motion, you've got these older frames that are starting to fade, moderate, middle frames, and then the more recent frames. So you see tick, tick, tick as the ball is moving. These frames are moving. The bank is moving, I would argue, within the real world schema because you brought your attention to the soccer ball. And if you bring your attention to your own body, then you could see these kind of frames of consciousness. Like, okay, my body was here at this, for this 100 millisecond frame. It was here for this 100 millisecond frame. It was here for this 100 millisecond frame. And so it's tracing out this path, and you know, because the body was moving, each frame is happening at a new location. And what's interesting about this diagram is that, okay, it shows you where exactly within the brain it thinks it's doing it. So this is parietal lobe here, but it's also got this other stuff of, like, you know, okay, the object related to the head, or self and object motion and orientation, body related to the vestibule, because you know, you've got your head direction, but you also have your torso direction. Like I said, the bank can come to the head, the bank can come to the torso. You can get these frames for posture. So it's a pretty interesting thing here. You also got the RSP is retrosplenial cortex sitting behind the hippocampus, is implicated in perhaps transforming egocentric 2D to allocentric 3D isometric skins. You've got head direction cells in the hippocampus. People have ostensibly found three-dimensional head direction cells, so that would be like, you know, you bringing the bank to the head and understanding exactly the orientational specificity of the head in terms of 3 dimensions. You got place cells, grid cells, border cells. Of course, hippocampus is a very interesting region. Very interesting diagram. I like this one. Getting close to the end here. So if we take existence, we break out the physical world, or the noumenal world, which we are never able to directly observe, I would argue. And Immanuel Kant also argues that. And then you've got the perceptual or phenomenal realm, and you can break this down into the movie projector, which would be like the context of consciousness, 10 hertz, all the variable 1 hertz to 1,000 hertz, and the content of consciousness, which would be like the movies playing, and generally going to be like 40 to 80 hertz. This, I would argue, is at least starts out as kind of this 2D sphere around you, and its pixels and its color and its location. Whereas this is going to be more like alignment and shape and storage of those shapes. So all of this is the bank. The 3D cursor is selected. 3D cursor is selected off the bank. The ring path is selected off the bank. The frame is selected. So this is all the bank here. And the bank is the tether between the two worlds. Sensory physical world is just another word for the real world schema. Cartoon motor world, just another word for the imagination schema. The cycles of consciousness can vary, like I said, 2 hertz to 1,000. So these various stages of 3D cursor to ring to frame that happen within a single cycle of consciousness could vary in duration based on what the current frequency of cycles of consciousness is. And last of all is a teaser for the next class, which is going to be on schemas. Here is a chart showing a lot of the schemas. In blue is shown the content of consciousness, which is this real world schema, imagination schema, dream world schema, each of which can be broken up. Real world can be broken into environment schema. It'd be like the ground and the objects around you. The avatar or perceptual or proprioception body schema is the mental representation of the location of your body. Imagination schema can be broken down into the imagined environment, as well as where are you viewing that environment from, so kind of a mind's eye schema. And then when you fall asleep, the sounds that you hear coming from the real world, you stop interpreting them according to their actual cause, and you start mapping them to these crazy, to your imagination, as if basically as if it was a part of your imagination. And so that's the transition from going from wake here to sleep, is you start mapping external stimuli all to your imagination. And also when you fall asleep, once you get to deeper sleep, the brain has mechanisms for shutting out the external stimuli of the world, in particular the audio, so that it's not bothering you and waking you up. But so the dream world's kind of like a hybrid, because it is your imagination, but it almost feels real, as if it's like the real world schema. So it's kind of like a strange hybrid. And so basically up here at the top, this yellow can be thought of as your bank schema. And it's kind of a little bit different from the rest, because this is actual shapes, 3D shapes here, 2D outlines, and at a slower rate. This is the context of consciousness, and the blue is the content of consciousness. But you could think of both of them as being schemas. When the bank schema comes and models the real world schema, you can get basically a 3D isometric model for some part of the real world, or for imagination, or for any of this stuff. So, you can still have 3D shape within these other schemas, but the bank has to get involved to give you explicit understanding of 3D shape or 2D shape. And then all of these would fit within a single fusing schema that basically tells you what orientation, scale, and position each of them are relative to the other, so that you just end up with one understood perceptual space. And like I said, we'll get into this more on the next class, and thank you for watching.